Hello, my name is Cameron Hicks, and this is my presentation about the charge tape experiments. In this experiment, we explored how electric forces between charged objects can become strong enough to balance gravity and cause one tape to float above another. After making measurements, we then built a computational model to predict the amount of charge needed to reproduce this behavior and compare the model with our observations. The basic physics principles include Newton's second law, gravitational force, and the electric force. First, gravitational force pulls the tape downward, which we calculate using the equation F equals m times g, where m is mass and g is the gravitational acceleration. Second, the electric force acts between the charged tapes according to Coulomb's law, which demonstrates that electric force depends on the amount of charge on each object and the distance between them. And when the tape floats steadily without accelerating upward or downward, the upward electric force balances with the downward gravitational force. And at this point, the net force is approximately zero, creating equilibrium. And understanding this force balance is key to estimating the amount of charge on the tape. To make calculations manageable, several simplifying assumptions were made. We treated each tape as though all its charge were concentrated at a single point in the center, even though the charge is actually spread along the tape. We also assume that the charge is evenly distributed and that both tapes carry roughly the same charge magnitude. Additionally, we ignored air resistance and assumed tapes remained aligned vertically, even though in reality they can move slightly. And these assumptions make modeling easier while still allowing predictions that are very reasonable and accurate compared to observations. And as far as the experimental setup goes, our tape length was about 8 inches or 2 meters, or 0.2 meters, excuse me. The estimated tape mass was 2 times 10 to the negative fourth kilograms, and the floating separation distance was 0.019 meters. And also we have the gravity force calculated from the tape mass and the electric force equals gravity when the floating occurs. For the observational data, we used two charged pieces of tape, and then we affixed one of those pieces of tape along two expo markers. And then we held the other tape, and then using that tape, we approached the first fixated tape with the expo markers. And then as you can see, the repulsion because of the charges on each tape was demonstrated here, and that was about 0.019 meters. Next, we built a computational model to simulate the interaction between the tapes. The program calculates the electric force between tapes using Coulomb's law while also including gravitational force acting downward. We adjust the charge value in the simulation until the upward electric force balanced gravity, matching the floating condition observed in the experiment. And this allowed us to estimate the magnitude of charge present on each tape. Although the model simplifies the real system, it reproduces more or less the behavior observed experimentally. The computational model predicted floating behavior similar to what we observed through the experiment. The separation distance and calculated forces from the simulation were close to the measured values, suggesting Coulomb's law provides a good description of the force involved. However, there were small differences that existed between the prediction and the observation, and these differences most likely arose from measurement uncertainty, assumptions, uneven charge distributions, or environmental effects such as air currents. And despite these small discrepancies, the simulation successfully reproduced the main behavior of the experiment, showing reasonable agreement between theory and observation. Possible errors include uneven or changing charge distribution, measurement uncertainty in distance, air resistance or drag force affecting tape stability, charge loss due to humidity or handling when tapes, and tape not behaving exactly as a point charge. And just some conceptual questions. If electrons had positive charge and protons had negative charge, the behavior we observed would remain the same. This is because the attraction or repulsion patterns would remain unchanged when in comparison with one another. Uh, it is also important to handle charged tapes as little as possible because touching them would allow charge to transfer away through your body or other objects, and this would reduce electric force and prevent the tape from floating. To conclude, this experiment demonstrated that electric force between charged tapes can balance gravity and cause one tape to float. By combining experimental measurements and computational modeling, we estimated the magnitude of charge on each tape. The model predictions and experimental observations showed reasonable agreement, confirming that Coulomb's law accurately describes forces involved. Overall, this lab demonstrated how experimentation and computational physics works together to explain real-world physical behavior. Thank you.